Okay, let's continue with the second part of multi-component distillation. Right. If previously for binary distillation, you have only two components, so you can separate the two components into two different purities. Let's say you have A and B, so you just have to separate the top product here contain mostly A and a small amount of B, and the bottom product mostly B and small amount of A. But for multi-component mixture, you have to decide what are the key components, because distillation of a multi-component mixture, they allow only the separation between the two components, I mean the split of the two components. So let's say if in this case you have the mixture of components A, B, C, and D. These are arranged according to their boiling point. So A being the most volatile component, followed by B and C, and finally D is the least volatile component, the highest boiling point. Okay, so we have to decide the two key components to be separated, okay, because we have to decide which one are the key components that is the split. So when we decide, it is according to the volatility. So light key, the two key components to be separated are called light key and heavy key. So light key, as the name implies, is the lighter component, i.e. the more volatile component, and then the heavy key is the less volatile component, and we put the subscript L for light key and the H for heavy key. So for example, if you have the system A, B, C, D here, we can decide to split this mixture into two like this. Okay, so we decide the split, the separation only between two components here, meaning we decide the split between component B and C. So when component B is the heavy key, I mean the light key, sorry. So light key is component B and heavy key is component C. So since B is the light key, so any compound that is more volatile than component B will follow component B to the top column. So if we decide this, so we can expect in the top column will contain mostly A and B, and then at the bottom of the column you have C and D, mostly C and D. Of course, there is no perfect separation, but hypothetically, this is what we aim to achieve in a multi-component distillation. Okay, so what else? So components more volatile than the light key are called the light components. So this is the light key B, so A is the light component. So A and B are the light components, and C and D are the heavy components. Components less volatile than the heavy key are called the heavy components. So the two key compounds are present in significant amounts in both the distillate and bottoms. So yeah, for a start, this is the arrangement for the multi-component distillation. But this is not necessarily the case. Let's say if you have A, B, C, D, it's not like you have to choose B as the light key and C as the heavy key. It could be that you want to choose B as the heavy key and A is the light key. So instead of splitting A, B, C, D like what you have here, so you would have A and then B, C, D. Well, depending on your heuristic, like what I mentioned in part 1, the arrangement of the distillation column. Or it could be that you want to have a split between C, ABC, and D components. So C is your light key and D is your heavy key. So you can have ABC here mostly and mostly D at the bottom. This could be one of the arrangements. So if you have A, B, C, D, 4 components, you have maybe you have 4 different arrangements of how you want to split the components in a multi-component distillation. All right, so to design a multi-component distillation tower, we have similar to the binary system, the limiting cases include the minimum number of stages and minimum reflux ratio. So let's go for minimum number of stages. As you can recall, minimum number of stages apply when there is a total reflux of in the column, meaning there is no product, so everything is being fed back to the column. However, if for binary distillation, previously in binary distillation at total reflux, you can determine the number of minimum stages using this diagram, right? The VLE, and then you decide the XD, and then the XD, then you just do the stepping of the stages like this, and this would be your minimum number of stages. However, for multi-component distillation, because we don't use the binary VLE curve for the equilibrium data, so we cannot use graphical method to calculate the minimum number of stages. So what we can do is to use the other method, which is the Penske equation. So the Penske equation can be applied for multi-component distillation by replacing the formula with this: x of light component in the distillate, x of heavy component in the distillate, x of heavy component in the bottom, and x of light component in the bottom. So all these x's are the mole fractions, and if it indicates L, meaning the light key, if it indicates LD, then D is distillate. And also the D and the B. So the D is the molar flow rate of the distillate, and for B is the molar flow rate of bottom product. Okay, so B and B here. Whereas the alpha, so alpha LD, alpha LD, here it should be bottom, sorry, so here should be LD. So alpha average is the what do you call it, geometric mean of the alpha light key in the distillate and alpha light key in the bottom product. Right? So you just have to identify what are the mole fractions of light key and heavy key in distillate and in the bottoms, and you need to know the flow rates of distillate and bottoms, and also you need to know the alpha values. Then you can key in the values in the Penske equation and get the number of minimum stages. So if you notice here, n min in this formula, n min equals to something 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 minus 1. So the minus 1 here indicate the reboiler. Some books you don't have the minus 1. So if in some books you have the Penske equation for multi-component distillation is the formula, the log something something divided by log something something without the minus 1, meaning that the n min is including the reboiler. So you have to be careful in that. Or if in some books it says here n min plus 1 equals to this part of the formula here, log something something here, meaning this plus 1 is the reboiler. So you have to be careful with that, and you have to know what does it mean for the different formulas of n min. It's not that it's wrong, but it's just that whether it includes or excludes or indicate the presence of reboiler. So there's a note here which says that the distillate temperature at the dew point and the bottom's temperature, i.e. the boiling point estimation, is partially trial and error, as what I have shown in part 1 of the lecture previously, since the distribution of other components in the distillate and bottoms is not known yet and can affect this value. So these are really preliminary, and you have to redo or recheck the calculation like iteration. So that's why for multi-component distillation it's better to use software, but we have to know the basics of the calculation before we just ask the software to do the job for us. All right. So before I proceed with what do we do when designing a multi-component distillation column, so let's just have an overview of the algorithm for multi-component distillation. So we start here where we specify the feed, or we have some specification of the feed composition. Okay, so for component, let's say A, B, C, and D, we know what are the X of A, X of B, X of C, X of D in the feed. So after we know the feed specification, we have to specify the split of two key components. So let's say if we identify the two key components, this one is the light key, B is the light key, and C is the heavy key. So we specify the split. Let's say for the column, we want 95% of the light key will be recovered in the top product, and the 95% of the heavy key will be recovered at the bottom product. And first assumption is to assume that all of A will be recovered in the top product because it's lighter than component B, and assume first that all of D will be recovered at the bottom product because it's heavier than component C. So if 95% of C is gonna be recovered in the bottom, so maybe all of D will be recovered at the bottom, but that is just an initial estimate. So that is the estimate splits of the non-key components here. So where we estimate the non-key component, the light key, and the heavy key. In the light components and the heavy components, we estimate the recovery of those components in the top and bottom products. Next is to determine the column pressure and the type of condenser. At this stage, maybe you are just given that the column pressure operates at a certain pressure, and then you can decide the type of condenser. And normally for this course, for these exercises, we are going to just use the total condenser. So here you need to determine the bubble point and dew point calculation of the column when you were already given the pressure and the composition of the top and bottom product. Then you do the flash at the column pressure, and then we use the Fenske equation to calculate the minimum number of theoretical stages, and also we still use the Fenske equation to calculate splits of the non-key components. Non-key components meaning the light components and the heavy components other than the light key and heavy key. Then we calculate the minimum reflux ratio, and that is going to be done using the Underwood equation. And next, after we know the N-min and R-min, we can calculate the actual theoretical stages for a specified reflux ratio. So here we got N-min, here we got R-min. So we have to decide what is our R. So typically R is between 1.2 and 1.5 times R min. So you have to decide or specify the reflux ratio to be how many times the minimum reflux ratio. Then after you have specified the actual reflux ratio, then you use the Gilliland correlation or any other correlation to calculate the actual theoretical stages. Then we need to also know the feed stage location. So to do that, we need to use the Kirkbride equation. And finally, after you have done all these, you have to calculate the condenser and reboiler duties using the energy balance equation, and you're done. Okay, I need to highlight something here where so after you have calculated the minimum number of stages, and then you use the Fenske equation again to calculate the splits of non-key components, you have to go back to the step here. Because, okay, when we calculate the bubble point or dew point calculation, these are just estimate because we are using the estimate splits of non-key components, because initially, remember, I said like we specify the split of two key components. Let's say for component B, we specify 95% of component B is recovered in the top product and 100% of component A is recovered in the top product. And then we specify 95% of component C is recovered in the bottom product and 100% of component B is recovered in the bottom product. But then we use these composition at the top column and the bottom column to calculate the bubble point and dew point calculation. But when we come to this stage and really calculate the splits, if it differs much from our initial estimate, then we need to repeat until we don't have a lot of difference anymore. So we will do that in the example to follow, but here is just to give you an overview of the algorithm or the flow process of designing a multi-component distillation column. So if you refer to some books, the multi-component distillation column design using shortcut method is also known as the FUG method. So what is F? Is the fence K. So the fence K is when we use this to calculate the n-min and also the split of multi-components. U is for underwood. So this one is to calculate the R-min, and G is for Gilliland. So just to familiarize you with all these terms. Okay. At total reflux for multi-component distillation, we can use the Fenske equation to calculate the distribution of other components in the tower. Okay, we can do this by using the Fenske equation. Modify the Fenske equation to replace the light key and heavy key components in the distillate and the bottom to be rearranged and written for any component I in the system to be in this way. So instead of XLD, you have XID, and instead of XLB, you have XIB. So this I here refers to any component A, B, C, or D in the system. So just replace all with I, so that you have the you can calculate what is the flow rates of component I in the top and flow rate of the component I in the bottom. So if you wonder where this equation comes from, it actually comes from this original Fenske equation for the multi-component distillation, where we have light key and heavy key. I won't bore you with the details of the derivation, but trust me that if you modify this Fenske equation into just component I, you will get this equation, but these terms here stay. The XHD, XHB here, it stays. So you can look it up on how to derive this equation to calculate the distribution of other components. Okay, so this concentration of other components determined at total reflux can be used as an approximation with finite and minimum reflux ratio. Actually, this is only one of the ways to calculate the distribution of other components. More accurate method, you can find it in the literature, but this is currently enough for the course now. So what do I mean when I keep saying the distribution of other components? Just to be clear to you, so let's say we have this column A, B, C, and D. So you have a certain composition. Let's just have some numbers for you to visualize. So let's say you have 25% of A, 25% of B, 25% of C, and 25% of D. So 100% in total for the feed. So you have in the column this distillate product and the reboiler. Okay, this is bottom product. So let's say you have 100 mole of feed, 100 mole per hour of feed. So 25% of B is 25 mole per hour, and 25 mole per hour of A, 25 mole per hour of everything basically. So if you initially specified to have B as the light key and C as the heavy key, so A will be the light component and D will be the heavy component. If you specify to have 90% of C recovered in the distillate product, so you will have component, so B. So meaning in the distillate product here, you have component A and component B. So And initially you will think, or you will estimate 100% of A will be recovered in the top product, meaning 25 mole of A will be here. And then only 90% of B will be here. So what happened to the C and D? And then at the bottom's product, you have also A, B, C, D. Okay, let's remove the A because we have assumed that A is 100% recovered in the top. So 25 more coming in, 25 more coming out at the top product. So there is no A in the bottom product. However, if you have 90% of B in the top product, then 10% of B must be appearing at the bottom product. So here you have 0.1 times 25 mole per hour of component B. And then C, let's say if you say that 90% of component C in the bottom, then you have 0.9 times 25 mole of C here. And then you have 10% in the top product. And then we also assume initial assumption is that 100% of D will be at the bottom product, so D is 25 mole. So then we don't have the component D in the top product. So this is our initial estimation. However, after you have calculated the minimum number of stages using the Fenske equation, this one, then you want to calculate the distribution of other components. Is it really 100% of A recovered in the top product and 100% of D recovered in the bottom product? Is it really that nothing, no D at all here and no A at all here? So you have to use this Fenske equation to calculate. We will do the example, don't worry. But this is the idea of what do we mean by calculating the distribution of other components using the modified Fenske equation for each component. So the I here you can replace with A and D and anything in your system. Okay. Okay, let's go to the first example for multi-component distillation. Actually, we only have example 1 throughout this lecture, but there are many parts of example 1. So let's do the first part of this example. So let's say you have a liquid feed to a distillation column at 405.3 kilopascal absolute. So this is about 4 atm. Fed to a distillation tower. The composition in mole fraction of the liquid feed is as follows. So you have butane, you have pentane, you have hexane, and you have heptane. These components are arranged by increasing boiling point. So N-butane is the most volatile component, followed by pentane, hexane, and finally heptane is the least volatile component. So you have the feed composition of component A, B, C, D. So here your component A is butane, this is your component B, this is your component C, and this is component D. So you have the XA, XB, XC, and XD. So you are asked to calculate. First, calculate the boiling point and the composition of vapor in equilibrium with the liquid feed. And then second part B is, if the liquid feed flows at 100 mole per hour at the boiling point of butane in A at 405.3 kilopascal and is fractionated so that 90% of the N-pentane component B in the feed is recovered in the distillate and 90% of the N-hexane component C in the feed is recovered in the bottoms, calculate number 1, moles per hour and composition of the distillate and bottoms. Number 2, the top temperature, i.e. the dew point of distillate and the boiling point of the bottoms. And number 3, calculate the minimum stages for total reflux and distribution of other components in the distillate and bottom. So we are going to use Fenske equation here and use the given K chart, the given chart for the K values. Okay, let's do that. So these are some examples of charts where you can read the K values from. So the first figure is equilibrium K values for light hydrocarbon system at 405.3 kilopascal absolute. So this is given also in Spectrum. I have uploaded the PDF file for you to just use it. This is particularly specific for this example. So if you notice, it's only 4 components here and it's conveniently given to you at the given pressure, but you don't necessarily have this privilege to the access to the K values like this. Sometimes you need to find your own K values at the given pressure at which temperature. So an example of a chart that you can use to do that is this chart at the right hand side here, which is called the Priester chart. I have also uploaded this Priester chart in the spectrum in PDF file. And if you notice, there are about, I think, 4 different charts with different temperature range and different units of pressure and temperature and different range of pressure. So what you can do is to, if you are not given a chart like this on the left hand side where you can easily read the K values at different temperatures, because this chart at the left hand side here is conveniently made for you at this pressure. But if you don't have something like that, so you have to read the pressure, let's say 405, so 400, about maybe here, and then at which temperature you want to read the K values at. So let's say I'm just trying to just show you how to read the chart. Okay, so at this pressure, let's say you want to read at temperature 90 degrees Celsius. So you have to connect 2 lines between this pressure and this temperature, and then you find out what is the K value for the component that you want to find. So let's say for butane. So for butane, then you go here for butane, then you go and read it. It's too small, but I think you can read it better when using your PDF file, but you can read the K values here. Then you can compare if the values of the K value that you got from this chart is the same with what you have with the chart on the left hand side. Okay, that's just, we're not really solving the problem yet. We are just reading the chart. We are just trying to read the chart. So you have to have a pressure and temperature, draw a line and read what are the K values for your hydrocarbon of interest. Okay, let's wrap this off first and focus on our example. You can have practice on how to read the deepest chart on your own. Okay, to actually solve part A of the example 1, so we have to recall in flash calculation how to find the boiling point of the component, of the mixture. So the boiling, to find the boiling point, you have to satisfy this equation. So you have A, B, C, D components. Let's say you use component C as the base component, then the equation becomes like this. So you have Kc as the constant outside. So calculate the boiling point using a trial and error process. So you have to assume the temperature, and then you calculate the K values from that temperature. Then you calculate the new K values of C, and then you find out the new temperature. If the K value of C is a lot of different from the initial gas, then you repeat until the temperature is not that much different anymore. And finally, after you have decided the final temperature, you can calculate the vapor composition. Okay, so we have gone through this in part 1. I'm not going to repeat it every step of the way, but we're going to just straight away show how to use it. So now that you have known all the steps, let's actually do it. So let's say we use this chart for the K values. So we just have to try the first temperature. So let's take T1 as 65 degrees Celsius as our first trial. So what you do is you just prepare a table so that you can just fill in the values when you have read the K values. So you have components A, B, C, and D. So you have Xi at the feet. Okay, so it's 0.4 for A, 0.25 for B, 0.2 for C, and 0.15 for component D. Then we put what are the K values for A, B, C, D, and then alpha I equals to Ki over Kc. Then we want to calculate what is alpha I Xi, so we put here. Alright, so 65 degrees Celsius, we read from the graph. So here is 50, 75, so 50, 55, 60, 65, 70. So 65 is here. So you should like draw a straight line to read the K values for each component. Okay. So for component A is butane. So you read the value of K values here. For N-pentane is here, hexane is here, and N-heptane is here. So actually you should draw a very straight line accurately. So let's say this example I've taken it from the book, Jane Copley's book. So you can refer to that book for if you want to revise in terms of written solution. Okay, so in this case, I just go through the solution again. So let's say we follow the book and take the values given from the book. So for component A, butane, you can try to read this graph here, but I don't think you will get the exact accurate value as what you will get in the book. So from the book, the K values for A is here is 1.68, and then for B is 0.63. Okay, here is about 0.63, and then for component C is 0.245, and for component D is 0.093. That's what is given from the book. You can check these values with other charts, like the Bristol chart. You should get almost the same value. Okay, next is we calculate the alpha. So alpha I equals to Ki over Kc. So alpha A is Ka over Kc. So you can punch the calculator to calculate what is Ka divided by Kc. So let's say you have done it and you got the values. So take the values. You can check the values if you do it on your own. 0.380. So next is you want to calculate what is the product of alpha I xi. So these are just the product of alpha I and alpha I and xi. So just multiply these two values and each row, and you shall get some numbers. So okay. So let's say we did the calculation, so you get alpha I xi is for this one 2.743, and then this one is 0.643, 0.2, and 0.380. So next is you calculate the summation of alpha I xi, so you just add all these numbers. So you get the summation. Here is 3.643. So what's next is you try to use this to calculate the new value of Kc. So the new value of Kc equals to 1 over summation of alpha I xi equals to 1 over 3.643 is about 0.2745. So this is the value of Kc equals to 0.2745. So you know that for component C, Kc, you need to find out what is the temperature such that the value of Kc is 0.2745. So for C, component C is hexane, here is 245. So maybe you can try to find, but according to the solution in the book, it's about 69 degrees Celsius. Okay, maybe about here. This is 0.2745. So i.e. this one meaning the temperature, second guess of the temperature is 69 degrees Celsius. 69 degrees Celsius. So what's next is that you try to repeat the same process again. So this time T2 is 69 degrees Celsius. So you repeat So for component A, B, C, and D, the xi remains the same, 0.4, 0.25, 0.2, and 0.15. And then you read the value of K for each component at 69 degrees Celsius. So if you just read the value, you shall get these values, just following the solution of the book anyway. So in an ideal world, this happens, but otherwise you should try to scramble the values from other charts. So after you get the K values, you get the alpha. So alpha is Ki over Kc. So Ka over Kc, in this case is 6.607. Here is 2.522. This is 1 plus Kc over Kc. And then here is 0.391. Then you repeat the same process. You calculate the summation, the product of alpha I and xi in this temperature. Okay, 0.631, 0.2, 0.059. Then you calculate the summation of this. You get 3.533. Okay, so then what you do again is you check the new values of Kc. So Kc equals to 1 over alpha xi, and what is that? And then you check what is the temperature for this value. So apologies, actually these values are read at the temperature of 70 degrees Celsius. Okay, so actually in this case, the first temperature you guess is 65 degrees Celsius. After you guess the 65 degrees Celsius, well, actually then you get the second temperature is 69 degrees Celsius. So by right, you should repeat the calculation for 69 degrees Celsius. What are the K values? What are the alpha? And what are the products of alpha xi? And then get the new Kc value. And then at the third trial, only you got T3 equals to 70 degrees Celsius. To confirm whether you should stop at T3, you should repeat it again, and you should calculate what are the K value. Then actually in this example, the temperature that you got at 70 degrees Celsius, at the new Kc, you got the still 70 degrees Celsius. So meaning that you can stop the iteration at this point, and then after you have stopped, it's not the end, because you need to calculate the vapor in equilibrium with the liquid product. Alright, so let's say we want to calculate the vapor composition in equilibrium with the liquid product. So you should refer back to the steps that in the previous slide just now. Wait until I finish rubbing this off, just like what we have in class. You just normally wait while I erase something. Okay, so yi is equal to alpha I xi divided by the summation of alpha I xi. So from here, you can calculate what is yi. So ya is actually this value divided by this value, so you get some number. In this case is 0.748, and then for yb you do the same, this value divided by this, and it's 0.178. Then yc is 0.057, and yd is 0.017. So be careful, and just to be sure, you can check if the summation of yi would be equal or close to 1. Alright? Alright, for part B of this example, so let's say if you have a liquid feed of 100 mole per hour, and then at the boiling point given in example, in the previous example, fed to the distillation tower at the given pressure for atm, and to be fractionated so that 90% of component B is recovered in the distillate, and the 90% of component C will be recovered in the bottom. So you have to calculate, number one, the moles per hour of composition and moles per hour and composition of distillate and bottoms. Okay, let's do that first. So you have the column. Okay, so you have the feed, and then you have the top and bottom product. So your feed is, let's say in this case, is 100 moles per hour. So you have A, B, C, D, butane, pentane, hexane, and heptane respectively. So you have here 40 moles, 25 moles per hour, 20 moles per hour, and 15 moles per hour, okay, for each component. So let's say we decide in this case what are the heavy key and the light key. So our light key in this case would be B, component B, and our heavy key in this case would be component C. So we decide the split of these two components in the fractionating tower. So we want here to be A and B, and here to be C and D. However, there will still be some amount of C left in here because in the question it says 90% of hexane or component C is recovered in the bottom, so there will be some 10% of C in the top. Same goes to component D, there will be some P present in the bottom product. So from here you can make an estimate and also an assumption what would be the mole per hour of each component. Okay, let's say if 90% of component B is at the top product. So the mole per hour of component B in the top product is then 0.9 times 25, which is 22.5. So here the component B is 22.5 and the remaining 10%, 2.5 mole of B will be in the bottom. At the same time, 90% of component C is at the bottom product. So the mole per hour of component C at the bottom product is 0.9 times 20, which is 18 mole per hour. So here you have 18 mole per hour of component C. And then because the feed is initially 20 mole per hour for component C, at the bottom is 18, so the remaining 2 mole per hour will appear in the top product. So what about components A and D? So for the first assumption, first trial of this assumption, let's assume that all component A will be recovered in the top product. So 40 mole per hour of A is in the feed, and all of them will appear in the top product. And the component B, same goes to component B, because it's heavier than component C. So let's assume that all component D appear in the bottom product. So this is our first guess for the distillate and bottoms product. So we can do part A, moles per hour of and composition of the distillate and bottom product. So the mole per hour of the distillate product is the summation of this. 40 plus 22.5 plus 2 equals to 64.5 mole per hour. And then for the mole per hour for bottom product is the summation of these three, which equals to 35.5 mole per hour. As for the composition, you can just calculate the xi at the top and the xi at the bottom. So you can also try to tabulate this into a table. You have component A, B, C, and D. In the feed, you have xi, and you have also xif, i.e. the molar flow rate of each component. Okay, and then at the distillate, and then at the bottom. So at xi at the distillate, and then B, and then xi at the bottom, and then B. So here it's a bit confusing because D and B is also component. There is also component B and component D. So you just have to not be confused. Okay. So I'm just filling up the numbers here to indicate the composition and flow rate of each component in the feed, the bottom, and the distillate. So what we have here is XIDD, XIDD. Okay. For component A, we have 40. Then for component B, 22.5. And for component C, we have 2. And for component D, we have 0 in the distillate product. So the total is 64.5. So you can calculate the mole fraction. So I'm sure you know how to do this. So I'm just going to give you the numbers here. 0.349, 0.031, and 0 component D. So this will give you a total of 1. As for the flow rate in the bottom, so there is no component A, so it's 0. For component B is 2.5 moles per hour in the bottom. Component C is 18 and component D is 15. So the total is 35.5, and then you can calculate the mole fraction of each component. So 0.007, 0.507 and 0.423, and make sure this all adds up to 1. Okay, so to help us proceed to the next part, we can put the composition of the top and bottom respectively. So you have here XIF of A, B, C, and D. A, B, C, D, 0.4, 0.25, 0.2, and 0.15. So F here is 100 mole per hour. So you have your distillate product is total up to 64.5 mole per hour. And then you have here, let's use Y in this case, because let's say we don't condense. Oh, it doesn't matter. Okay, it's just the composition anyway. So for component A is 0.62, 0.349 for component B, and 0.031 for component D, and 0 C, and 0 for component D. So A, B, C, and D. And at the bottom, we have flow rate is 35.5 mole per hour, and the xi for each component A, B, C, D are 0 for component A, and 0.07 for component B, 0.507 for component C, and 0.423 for component D. The question in the second part of part B is to calculate the top temperature, i.e. the dew point of the distillate and the boiling point of the bottom. So let's do part 1. The first part is the dew point, okay? Dew point of the distillate product. So as usual, you have to guess the temperature. So just now you have calculated the boiling point of the feed, and the boiling point of the feed here is 70 degrees Celsius. So we have to assume a temperature lower than 70 degrees Celsius for the dew point. And also for the bottom, it has to be greater than the two temperatures. Okay, so to calculate the dew point, you have to prepare a table. So A, B, and C, and just to be sure, just put component D. So Yi at the top, at the distillate product, is 0.620, 0.349, 0.031, and 0 for D. And then you have to calculate a Ki for the temperature that you are guessing. And then after you calculate the Ki, you get the alpha I. And to calculate the dew point, you have to have this value, Yi over alpha I, and then the summation of Yi over alpha I later. So what would be the temperature that we would guess in this case? Okay, let's assume we get lucky because we are just following the examples from the book. So let's assume T1 equals to 67 degrees Celsius. And then if you read the chart that was given to you previously, You can read from the temperature 67 degrees Celsius what are the values of K for ABCD. So 1.75 for A and 0.65 for component B, 0.26 for component C, and 0.1 for component D. Now just to complete the exercise, okay? So alpha I is just Ki over Kc, and then you can key in the values. Here is 6.73, 2.50, 1, and 0.385. Then you calculate what would be the yi divided by alpha I for each component. Then you key in the values in the table, 0.0921, 0.1396, 0.031, and 0. Then you calculate the summation of these values. You get 0.2627. So just you need to check what is the new Kc. So the new Kc would be just summation of yi alpha I. The new Kc is 0.2627. So if you notice, this new Kc is very close to the old Kc that we used. So you can say that temperature equal to 67 degrees Celsius is the dew point for the distillate product. And then you can use that to calculate the Xi. So for this dew point, Xi is equal to yi over alpha I divided by the summation of yi over alpha I. So you can do that here to calculate the mole fraction of the liquid in equilibrium with the vapor. So if you do that, you can get the numbers 0.351, 0.531, 0.118, and 0 for D, and make sure this all adds up to 1 as the mole fraction. So this is how you calculate the dew point of the distillate by using the composition that you estimated earlier. Okay. Okay, for the second part of part B, which is to calculate the boiling point of the bottoms product. So I'm not going to go through again because I've shown you 2 times already how to calculate the boiling point of a multi-component mixture by reading the K values at a certain temperature and so on and so on. So I'm just going to highlight here. Okay, so you have the bottom product of 35.5 mole per hour with the composition as given for A, B, C, and D. So this table is taken straight out of the textbook of which the example comes from. So at first they tried with the temperature T1 equals to 135 degrees Celsius. Then they checked the K values. Then they come up with the second temperature, which is 132 degrees Celsius. And these are the values, the K values that they've got using temperature equal to 132 degrees Celsius. So if you, and then they repeat the same process again. So after they get the K values, they calculate the alpha I, and then what are the product of alpha I xi and the summation of alpha I xi. And finally, they check the value of Kc, which is now 1.144 compared to the old Kc 132, 1.15, that is close enough to 1.144. So the final temperature of the boiling point of this bottom product remains at T equals to 132 degrees Celsius. So after they've decided that this is the final temperature of the boiling point, you can proceed to calculate the yi, i.e. the vapor phase composition in equilibrium with the liquid product. So these are the yi. So that is how they calculated the bottom product boiling point. So you can try this on your own. Try using the first temperature and try if you can get the second temperature equal to 132 or close to that. Alright. Alright, for the next part of the question, we want to calculate the minimum number of stages for this system using the Penske equation. So you have this column, you have calculated the distillate product and the bottoms product, and this is the summary of the result, the final result. So the compositions are given here, and then the compositions, the K values at the dew point for the distillate product, the alpha, and the corresponding equilibrium composition. And also for the bottoms product, we have finalized the composition, the K values, the alpha, and everything. So bear in mind these for the distillate product, the dew point is 67 degrees Celsius, whereas for the bottom product, the boiling point is 132 degrees Celsius as what we have discussed earlier. So we're going to use the Penske equation to calculate the minimum number of theoretical stages. So this is the Penske equation that we have shown in this slide. So bearing in mind the -1 here, meaning it has excluded straight away the reboiler. Okay, so now what you have to do is you have to identify what are the values for XLD, D, XHD, XHB, XLD, and the relative volatility. Okay, so the relative volatility average is actually the geometric mean of the alpha L at the top and alpha L at the bottom product. So from the table given here, you can read that alpha LD equals to, so our L light component is component B, so you can read here, so the alpha LD is 2.5 and alpha LB at the bottom is, will be here, is 2.043. So alpha L average is thus square root of the product of 2.5 times 2.043 equal to 2.258. So this is the value that you're going to use for the alpha L average. And then for the XLD is the X of the light component in the distillate product. So it doesn't matter whether it's Y or X, it's just the composition. So XLD will be equal to 0.349. The D is the flow rate of the distillate. So the flow rate of the distillate is previously 64.5 here, and flow rate of the bottom product is 35.5 here. XHD is X of the heavy compound in the distillate product, so that would be this one. XHB, X of the heavy product in the bottom product, which is heavy bottom, this one, XHB, and XHD is XL. Let's see, it's a lot of notation here, so you need to be careful. So XLB is this value. So I want you to try putting in the numbers and calculate the number of theoretical stages, because you're given the formula and you have been shown what are the values. So all you have to do is really just to key in the numbers. It's not really that hard to think. And I'm just going to give you the final answer. Minimum number of theoretical stages is 4.404 trays. Okay, if I want to be more explicit, I'm just going to put excluding reboiler. Okay, see if you get the same answer. Okay, for the next part of the questions, we're going to estimate the distribution of other components in the top and bottom product. Previously, this table here shows our initial estimate, where we have the feed composition. This is our given feed composition. So we have 100 mole per hour of feed with the following composition of A, B, C, and D. And then we have assumed that all A appears in the top product. So 40 mole of A feed, 40 mole of A appears in the top product, and all B, 15 mole per hour of D in the feed, and all appears in the bottom product, 15 mole per hour of D. And then this is our initial estimate, and then we use this to also calculate the boiling point and the dew point of the dew point of the distillate product and the boiling point of the bottom product using this estimate here and this estimate here to calculate the. Okay, so these are all estimates. But now we want to know the actual distribution of components of other components, meaning the 90% of B appears in the distillate is okay, and 90% of C appears in the bottom is also okay. However, what about the A and D? Because previously we assumed that all A in the top and all D in the bottom, but is that correct? So we have to recheck that assumption. So we're going to use the Fenster equation to distribute the, to calculate the distribution of other components. So you've seen this in the previous slides. Okay, so I here we can replace for component A and component D. So let's do for component A first. Okay, so let's do for component A. We want to know how component A distributes in the top and bottom product. So alpha A average equals to the geometric mean of alpha A in the top and alpha A in the bottom. So from this you can, to get the value of alpha A in the distillate, you can read this table here, the second table. So alpha A is 6.73. This is 6.73, and alpha B, alpha A at the bottom is 4.348. So the average would be the geometric mean of these two values, okay, which equals to 5.409. Next, we use this formula XADB XABB equals to alpha A average times n min plus 1 XHDD XHBB. Okay, so the n min plus 1 just now previously you have calculated equals to 5.404 theoretical trace. And then XADD, this is what you want to find basically. XABB equal to 5.409 to the power of 5.404, and then multiply with XHDD. So the heavy component in the distillate is this 0.031 times D 64.5 divided by XH in the bottom 0.507 times 35.5. Then you get something to the value of 1017. Okay, so you have XAD D over XAB B equals to 1017. And then from material balance of component A, XAF F equals to XAD D plus XAB B. So XAF in the feed you have 40 mole per hour equals to XAD D plus XAB D. So you have two equations. This is one equation. This is two equations. Okay, so you solve equations 1 and 2 to get XADD and XABB, and then so if you solve these two equations, you get XADD is 39.961 and XABB equal to 0.039. So our initial estimate was that XADD equals to 40 and XABB equals to 0. Okay, so there's some difference between the initial estimate and the actual distribution. Okay, so you repeat the same process for component D. Right, so we repeat the same process for component D. Just now we did for component A, so now component D. So XDD D over XDB B equal to alpha D average to the power of n min plus 1, and then multiply with XHD D over XHB B. So now we need to calculate what is alpha D average. So it's the geometric mean of alpha D at the distillate and alpha D at the bottom. So you can refer these values to from the table from the previous slide. Okay, you should get these numbers equal to 0.452. So you can put this into this formula. 0.452 to the power of 5.404 times the compositions here. Refer to the table previously also. 64.5 over 0.507, 35.5, approximately equal to 0.001521. So you have XDD over XDB equals to 0.001521. Okay, then from component balance of D, so from XD in the feed times F equals to XDBB plus XBBB. So you know that there is 15 mole per hour in the feed equals to XDDD plus XDBB. So this gives you two equations. This is equation 1, this is equation 2, two equations, two unknown. Work this out to solve for XDDD and XDBB. So this is just algebra. So you should get these numbers. And then 14.977. Compare this to the initial estimate that we did before. Previously, we assumed that all D comes out in the bottom, so XDBP is 15, and then no D appears in the top product, so initially we assume this to be 0. Okay, so after you use the Pensky equation to calculate the distribution of other components, so you get the revised distillate and bottoms composition in the table below. Okay, you can see that instead of 40 moles of A coming in and 40 moles of A coming out at the top, you got only 39.961 of A in the top product, and the remaining A 0.039 mole per hour of A comes out in the bottom. For component D, initially we assume that no component D appears in the top, but actually there is about 0.023, and not all 15 mole per hour of D appears in the bottom, only 14.977 moles of D appears in the bottom. This one compared to our initial estimate before, right? So what do we do now after we found out that, okay, maybe to you, I don't know, you want to assume this is close enough or not close enough?